This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Hey guys, welcome to Lecture 5. Just a bit of announcement. So, as you all know, that tutorials will start next week. Now, can anyone tell me if they are registered in tutorials on Thursday, 9 a.m. and 2:15? Anyone here registered in these sessions? No? Right, so these tutorial sessions are quite empty, all right? So please, if you are able to move from your current tutorial session to this session. Okay. Do you all have classes on Thursday at these times? Most of you have it? Oh, okay. All right, so those of you who are not having any lectures, please go to these sessions, all right? If not, Carol will automatically shift some of you to those classes. Okay, the reason being is the other tutorial sessions are pretty full. It's at max capacity, and these sessions, on the other hand, are pretty empty. Okay, so if you want, I guess, more attention from the tutors, please go to these sessions. Right? Now, Carol has also informed me that more F4 labs have been added. It's probably not reflected on your timetable yet, so give it a few days, but it should be coming up soon. All right? Yep. Sorry, classes with? Oh, you mean for the Thursday? Yeah, I guess so. When you're doing the F4 lab, because it's only one F4 lab which you have to attend, right? So you might have to change to a different tutorial for that week. Yeah, because tutorials run from week 3 till week 13, right? But the F4 lab is only just one particular week. So maybe for that week you might just visit another tutorial session. Yeah. Okay. All right. So, a bit of recap on what we did in the previous lecture. So, using the stream function, we are able to simplify our Euler's equation, all right? And we derive the Helmholtz equation, which basically states that the total derivative of the Laplacian of psi, the stream function, is equals to 0. Okay? And as long as this Helmholtz equation is satisfied, we automatically satisfy continuity and also our momentum equation, right, for a two-dimensional, incompressible, and inviscid flow. So what's the physical meaning of the Laplacian of psi? We showed it in the previous lecture that it's basically just equals to the negative of vorticity, right? So to satisfy the Helmholtz equation, the Laplacian of psi can be equal to a constant or 0, right? But in this course, we are going to consider only the condition where the Laplacian of psi is 0, okay? Which basically means that the flow has to be irrotational. All right? So if the flow is irrotational, the stream function will automatically satisfy the Laplace equation, and therefore it satisfies our Helmholtz equation, which satisfies our continuity and momentum equations. Right? The next question we ask is then, does our simple flow satisfy the Laplace equation? Right? Does our source, our uniform parallel flow, does our sink satisfy the Laplace equation? And they do. Okay? Now, another question which we had to ask was, are we able to sum up these simple flows? So if I have a source and a sink, can I sum them up? And will I still conserve momentum and continuity? And because the Laplace equation is linear, okay, we showed that we can sum simple flows. Right, and I probably didn't emphasize how important this is, right? But this basically means, right, we can simply add irrotational flows to build more complex flow solutions. Okay, so that's what we're going to do in potential flow. Right, we're going to use simple flows such as a source sink, a point vortex, which we'll learn later on, right, to simulate or to model these complex flows. Now, going back to our smoker's problem, we are again going to model our exhaust as a sink, okay, and our smokers as a source. Right, and I can define my axis for x as being the horizontal axis and y the vertical, and the origin is at 0, 0 there, at the bottom left corner. Okay, and this is our stream function for a source and sink. Now, so subscript S, right, psi subscript S is for the smoker, right, for the source, and psi subscript E is for the sink, or the exhaust or extraction, right, and QS and QE are basically our volume flow rate, right, or our strength of our source and sink. Okay, but remember that this is located at our origin, 0, 0, okay, and that's not where we want our source and sinks to be. Okay, so what we have to do is we have to set an offset, defined as y0 and x0, okay, where x0 and y0 are our new origins. Everyone agree with that? Yep. Okay, so all I have to do then is to place my source, okay. Now we know that x0 is equal to 0, okay, because it's along the y-axis, right? So there's no x offset, and it's located at some height ly. ls. Okay, so I've just replaced y0 with ls. Okay, so it's y minus ls. And similarly for our sink or extraction fan, okay, again x0 is 0 because it's along the y-axis. Okay, and y0 here, that's just LE. Okay, that's the height. LE. Everyone follow so far? Yep, good. So my stream function for this flow is just going to be the stream function for my source plus the stream function of my extraction fan. Okay. Right, so I'll just rewritten it as such. Okay, so now we want to plot the streamlines for this flow, and we know streamlines are just lines of constant psi. Okay, so C, our constant, is equals to our stream function. Okay, and in MATLAB, it is very easy to visualize this flow. Okay, so the first step is to set up our X and Y grid. So in MATLAB, there's this function called mesh grid. Has anyone used mesh grid before? Yes, some of you have. All right, so mesh grid basically accepts a 1D array, two 1D array. Okay, so this basically says I want my x-axis to range from -10 to 10 with 0.2 interval. All right, and my y-axis to range from -2 to 10 with 0.2 intervals. Okay, and this will generate a 2D matrix for x and y. Right, and it will look something like this. Okay, so you can see that x and y. So x and y are my 2D matrix. Okay, both have the same size. So x contains the location of the x points, okay, and y contains the location of the y coordinates. Right, and I can also type my stream function psi in MATLAB. It looks something like this, okay, which is basically just this equation at the top there, right? And all I have to do next is to use p-color, right, to plot the contour of psi. So p-color x, y, my grid, and psi. Right, and you have something that looks like this. Okay. Now, I can use contour F as well. Okay, and I can set the contour levels. Okay, and if I use contour F, I can then see these lines of constant psi, right? Which are my what's lines of constant psi? Streamlines. Okay, good. So these are basically my streamlines, right? And hopefully you can see that flow is coming out here and going in here. And these are the arrows showing the flow direction. Okay? Right. Now, from my stream function, I can also calculate my velocity u and v, right? So remember our definition of a stream function. All I have to do then is to differentiate psi with respect to x and y. Okay, so I've jumped a couple of steps, but if you do that differentiation, you get an expression for u. Okay, and similarly, I can get an expression for v. Okay, don't worry too much about this. We'll do an example together later on. Okay. Right, so having the velocity u and v, okay, I can then plot my velocity vectors. Okay, and in MATLAB it's also very easy. All I have to do is just use the quiver function, which takes in my grid again xy and my velocities u and v, which are also a 2D matrix. Okay. So if I plot quiver, okay, you can see this velocity vectors, okay, flowing out from the source and flowing into the sink. Now, if I take these velocity vectors, okay, I can release a bunch of smoke particles by the smoker, and I can track this, the motion of these particles as well. Okay, and I can do that because I know that u is just equals to del x over del t, right? And using an Eulerian scheme, right, a first order time stepping scheme, it basically says that the new position of my particle, all right, is going to be equal to the old position of the particle plus some small time step, right, times the velocity of the particle. Okay? Right, and the lines traced out by these particles are called path lines. And because the flow is steady, okay, it does not change with time, our path lines are our streamlines. Okay? Right, so let's have a look at, oops. Okay, so we have a MATLAB code here. Oh, I can't see. My neck is going to break. Let me see. All right, so here we have our smokers. Oops, where's my pointer? Okay, you can see the smokers, all right, and a bystander is located some distance away. Okay, and in this code here, I've set the source, which are the smokers, and the sink, which is the exhaust fan, to have the same strength, right? So QE and QS are equal to 1, are the same, right? So if I release the particles, hold on a second, let me see where's my pointer. Hold on a second. Where's my... It's here. Okay, so if I release the particles, okay, do you think the smoke particles are going to hit the bystander? Yes or no? So this bystander is allergic to the smoke, all right? And if the smoke particles hit him, he's going to die. Okay. What do you think? It's going to hit him? Yeah. Okay. So he gets hit by this secondhand smoke and dies. All right. Okay. So, unfortunately, the bystander gets smoked. Okay. And that's not good. Okay. But now, there's one major problem with what I showed you just now. Can anybody tell me what's the major issue with this model which we have created? Sorry? The streamline, yeah? Exactly, right? So, streamline goes through the ground, okay? And that's not physical, right? There's no flow that can go through the ground, right? So, our boundary condition at the floor, right, is not correct. Right, and if you look at the velocity vectors, you can see that there's velocity coming in and out of the floor, which is not correct. Now, so we want to make our floor impermeable, right? Basically, there's no normal velocity in or out from the wall. Okay, and how do you think we can achieve this? Right, so the short answer is the method of images. Okay, and basically is we create a mirror image of all the flow features behind or beneath the required boundary. Okay, and this essentially ensures that the boundary becomes a streamline. Right, so what do we know about a streamline? There is no velocity component perpendicular to a streamline, right? No velocity can cross a streamline. Okay, so basically the method of images says that if, let's say, I have a source located some distance above the floor, okay, which is LS, the method of images says that I need to have an image with the same strength, okay, same strength as this one here, but it's located beneath the floor. So this is my mirror image here. Okay, and if I look at the streamlines now, you can see that the streamlines of my source does not cross this wall or this floor. And similarly, the streamlines of the image is the same, it's just a mirror image of the streamlines of the source. Okay. Again, we'll do an example of this, so don't worry too much for now. So let's just check, all right? So let's see what our velocities are, okay? So I can plot my velocities u, okay? I can also derive my velocities v, okay? So the velocities for this stream function looks like that, okay? And I can then analyze whether my velocity v is indeed 0 at my boundary or at my wall. So at my wall or my floor, when y is equals to 0, all I have to do is I substitute y equals to 0 to my v velocity. Okay, and you can see that it cancels out. And you can see that these terms cancel out as well. And therefore, yes, okay, there's my impermeable boundary condition is satisfied. Okay, so v is equals to 0 at this boundary here, at this floor. Okay. So the method of images work. Okay. The next thing I want to look at is the velocity u. Okay, again considering the velocity at the solid boundary, so y equals to 0. Okay, and I can simplify this equation for u a little bit more. And can you tell me when the velocity u is equals to 0 at the boundary from this equation? When x equals to 0. Okay, so u is only 0 at x equals to 0. Okay, but along everywhere along the boundary it is non-zero, my u velocity. Okay, and when we have a location where both my velocities u and v are 0, we have this point known as a stagnation point, right? Which is in red there. Okay, so my stagnation point is located at the origin, 0, 0, because my velocities u and v are 0 there. Now, a streamline which passes through a stagnation point is called a separatrix. Okay, so these red lines here, these are streamlines, but there are special streamlines called a separatrix because they cross through the stagnation point. Okay? Okay, now for irrotational and incompressible flow, all the stagnation points will be saddle points. Okay, so basically you have two velocity vectors coming out from the saddle point and two coming in. Okay? Sorry, stagnation point, coming out from a stagnation point. Coming out and coming in. See, so for this particular case again, right, you can see that there are velocities coming in from the top and bottom to the stagnation point, and velocities are coming out from the stagnation point on the left and right. Okay, so it has to be a saddle point. So in the exam, if you're asked to plot the stagnation point and the separatrix, one way of checking whether you have calculated or have drawn your stagnation point or separatrix correctly is that it has to be a saddle point. Okay, if you have 4 velocity vectors going into your stagnation point, it means that you have done a mistake somewhere in your calculation. Okay? Is everyone clear so far? Good? Am I going too fast? All right? Okay, good. So, the next question I want to ask is, what happens if I have a boundary at the bottom and at the top? All right, so I will need to have then 2 images, right? So I need to have one image for the bottom boundary, right? And I need to have another image for the top boundary, you would think, right? Okay, so then my stream function will look something like this, okay, where I have one for the bottom image and one for the top image. And my origin is here, by the way, all right? This is my origin. Okay, everyone agree with this? Yep. Now, if I consider the vertical velocity at y equals to 0, okay, at the origin, now you can see that these terms do not sum up to 0. Okay, and it basically means that my streamlines crosses my boundary. Okay, and the reason is because we actually have not included all images. Okay, so if I have a look at this boundary at the bottom here, right? How many images do you think I should have actually? I have one source here and another source here. So I should have two sources, right? So I'm actually missing one source at the bottom here. Okay. But, okay, and if I look at the velocity now, my vertical velocity, you can see that my vertical velocity is now equals to 0. But what's the other problem? Right, so now my top boundary is permeable. Okay, so I have a problem with my top boundary now. Okay, and that's because we have not included all the sources for my top boundary. So I need to have 1, 2, 3, right? So basically, if I want to make, if I want to have two boundary conditions, sorry, if I want to have two walls at the top and bottom, I will need to have infinite number of images. Okay, so the method of images basically just breaks down for this case, right? So it doesn't work when you have two walls, two parallel walls. Okay, right? So you see, I need to have a lot of sources. Okay, and this is similar to you looking at a mirror. Okay, when you have a mirror behind you, okay, you're gonna have a lot of reflections of your own image. Okay. All right, so we're going to deal with only one boundary, okay? No two parallel boundaries. Now, going back to the smoker's problem, can anybody tell me how many images I need for this case so that my floor is impermeable? One, two, three, 4. So you want to make this here impermeable. So this is going to be your boundary, right? And you have one source, one sink. So how many images do you think you need? 2, right? Very good. Right? So you need to have one image for the source and one image for the sink. Okay? And it has to be located below, right? Exactly opposite to your source and sink. Okay, so let's try and do this problem together. All right, so my stream function now has 4 terms, all right? I don't know why it's clipping the top bit. Okay. Right, so my stream function is going to be equal to psi s, which is for my source or for my smokers, plus psi e, which is for the extraction fan, okay, plus psi s I, which is for my image of my source, right, or my smokers, plus psi e I, which is the image for my extraction fan. Okay, so if I write it all out, I'm going to get Qs over 2 pi arctan y minus ls divided by x plus arctan y plus ls over x. Okay, so this is my image, right? Plus, oops, not plus, but minus QE over 2 pi. Right, these are my exhausts, right? Arctan y minus LE over x plus arctan y plus LE over x. Okay, and again, these terms, which I've labeled in red, they are your images. Okay, so what we're going to do next is we want to find our velocities u and v. Okay, and hopefully you remember again, you have to know this by heart. U is just del psi, del y. V is equals to negative del psi, del x. Okay, so u is going to be equal to del psi, del y, which is then going to be equal to qs over 2 pi 1 over, right, so we have to differentiate arctan, right, with respect to y. So we y minus le over x squared plus 1 sorry? Oh, sorry, yeah, that's ls. Thanks for that. Okay, and I have another term which is 1 over x. Do you all know how I got this? Yes? No? Oh no. Okay. Right, so I'm going to put a small note here. Okay, d over dx arctan u is just equals to 1 over u squared plus 1 u prime. Okay, so that's all I've done. I didn't do anything fancy, okay? So when I differentiate arctangent of this, so this is my u, therefore I get u squared here, right? And u prime for this one, because I'm differentiating it with respect to y, I just get 1 over x. Okay? Clear? Good. Awesome. So I'm going to differentiate all the other arctangent terms as well. Okay? And if you think I'm going too fast, just ask me to slow down. Okay? So I'm going to get 1 over, again I'm going to get y plus ls over x squared plus 1 over x. Oops. Okay, so minus QE over 2 pi (1 over y minus LE over x squared plus 1 over x plus 1 y plus LE over x squared plus 1 over x. Okay, so once you do it, you get, I guess you can see it's a bit repetitive. Okay, so I can simplify this, all these terms. I'll just put it as a side note as well, okay? But hopefully you all can see that that simplifies to x squared y minus ls squared plus x squared 1 over x, right? Right, everyone agree me for that? Yep, so what I'm going to get for u, right? So u is just going to be q over 2 pi x y minus ls squared plus x squared plus x y plus ls squared plus x squared okay, and it's going to be minus q, sorry, this is qs by the way, minus qe 2 pi bracket x divided by y minus le squared plus x squared plus x y plus le squared plus x squared. Okay, everyone follow? Yep. Do you all like me to write on the screen? Or do you just prefer me to just go through the slides? This is good? Alright, so you guys understand? Okay, good. And you guys get to embarrass me as well if I make any mistakes. So, it's good. But, yeah, so you can see that's how you get the velocity u, alright? And don't worry, you'll be doing more practices and exercise in the tutorials as well. So I'm just going to call this equation 1. And similarly, I can do the same thing to find my velocity v. Okay? So since everyone understands how I got my velocity u, okay, velocity v is going to be very easy as well. Okay, you all can do it at home. I'll show you the results here. Okay, so, oops, not psi, it's v, del psi over del x. Okay, so you get these terms for your source, for both the source and the image of a source, and minus q, yeah, correct, e 2 pi, it's going to be y minus le, squared plus x squared plus y plus le squared plus x squared. Oh, that looks like an e, I'll just put it s. Okay, and this is going to be my equation 2. So, once I have my velocities, the next thing that I want to do is I want to analyze my stagnation points and separatrix. I want to find where are they located. Oops. Okay, so the first thing I want to do is I want to consider along the x-axis. Okay, so what's y along the x-axis? Y equals to 0. Very good. Okay, so basically what I want to substitute y equals to 0 into my equations 1 and 2. So if I do that for equation 2, what's my v, my vertical velocity, going to be? If I substitute y equals to 0 into this equation. So this is 0, this is 0, this is 0, this is 0, and all the other terms which are y. So it's going to be 0. Very good. Okay, so v is going to be equal to 0. And that's good news, right? Because our boundary is impermeable. Right? Which is good. Before that, we had velocities going in and out from our floor. But now, we have managed to satisfy the impermeable boundary condition at the bottom. Okay, so we have looked at equation 2. Now, how about equation 1? I don't have equation 1 here, but what's going to happen to equation 1? Okay, so if I go back to my, no, not there, here. Okay, so I go back to equation 1. So I substitute y equals to 0. Okay, so these terms are going to add up, right? Because I'm going to get negative ls squared, and this is just ls squared, so my denominators are the same. I can just sum it up, and it's same for here. So I'm going to get, what am I doing here? Ugh. So I'm going to get u equals to qs over pi to, just x over ls squared plus x squared minus qe over pi x over le squared plus x squared. Okay? And my stagnation point, okay, is when my velocity u and v is equals to 0. Right? So I'm going to set my velocity u to be equal to 0. So therefore, for for u to be 0, this term has to be equal to this term, right? So I'm going to rewrite it as qs xs over l s squared plus xs squared equals to qe xs over LE squared plus XS squared. Yes, exactly. Very good. So I've rewritten XS to be the stagnation location, right? Very good. Okay, and hopefully from this equation you can see that my stagnation point occurs when XS is equal to zero. Okay. Okay. So XS equals to 0 is one stagnation point, right? But it's not the only stagnation point. Okay? So the other stagnation point is when I rearrange this equation a bit. So I can take this to the other side. Sorry, but no, I'm going to take this to the other side. All right, and I'm going to rearrange this so that it comes on top. So I'm going to get QE over QS LS squared plus XS squared to be equal to LE squared plus XS squared. Okay? Does everyone know how I did that? Okay, I'm just basically just rearranging my equation. Right, and I want to factorize XS squared, and that would give me QE over QS minus 1 okay, and it's going to be equal to LE squared minus QE over QS LS squared. Okay, again, all I've done is just rearranging my terms, nothing special. Okay, and I want to express everything, I want to have an expression for XS so that I can find my stagnation point. Okay, so therefore my XS is going to be equal to plus minus, oh, it's a bigger square root, so I'm going to, okay, that's going to be LE squared minus QE over QS LS squared. Oops. Over QE over QS minus 1. Okay, so basically I've expressed XS in terms of QE, which is the strength of the exhaust or extraction fan, in terms of the strength of the source and also my heights of the source and extraction fan. Okay, so this is very important. I'm going to rewrite this here. Okay, so everyone know how I got this, right? I know how I got this expression here for the stagnation point. So let's have a look at this term here. So basically, right, our stagnation point depends on this ratio, right? How strong the exhaust is or the sink is compared to the source. Okay, so I'm going to write a few conditions down. So when QE over QS is less than 1, okay, if it's less than 1, can you tell me what's going to have to the numerator? Is the numerator positive or negative when it's less than 1? It's going to be positive, right? Okay, because your extraction fan is located higher than the smokers. So this term here is going to be bigger than this term here because this is less than 1, correct? Right, so my numerator is positive. Okay. How about my denominator? Very good. So my denominator, on the other hand, is negative. Okay, so this term here is smaller than 1, so this whole term is going to be negative. Now, that's a problem, right? Can you have a square root of a negative number? Yes? Can you have a square root of a negative number? Yes? No. All right? You can't. Never. All right? So, no real solution. Okay, and in this case, it basically means that bystander will be smoked. Okay? So your exhaust fan is not strong enough. Okay, your extraction fan or your sink is not strong enough to suck up all the smoke. Okay, another condition, when QE over QS is greater than 1. Everything's fine, right? Then you have a positive value, right? So there is a real solution. Well, that's actually not quite true, okay? Because if this term here, right, if this term is very big, what's this going to be? Negative, and then you have the same problem as well. So, actually, if QE over QS is greater than LE squared over LS squared, we actually don't have any real solution.